Okay, so welcome everyone for the Symmetry seminar. I wrote it in the email, but we'll take a break during the KITP program. So for the next 2 months or so, we'll have no Symmetry seminar talks, but the KITP program talks are broadcast and also recorded. And we'll put the link into the Symmetry seminar page as well. Okay, Andrea, take you on.
Okay, so thanks to everybody for coming to this last seminar before the program. And today we are very happy to have Zohar Komargodski that will tell us about disclination, dislocation, and emanant flux Dirac criticality. Take it away.
Okay, thank you for everybody for coming. Very excited to give this talk. The first half would actually be a review. Maybe some of you have heard subset of it. It will have some new results, but mostly a review. And then in the second half, I'll talk about the newer paper that is the main subject of this talk. But I'll start with a general review of extended operators and defects in quantum field theory. And yeah, of course, at any point, just stop me with comments, questions, corrections, etc. So the first part is mostly based on works with Gabriel, Mark, and Avia, and also some work in progress with other people now. And the second part is on a very recent paper with Sam, Chris, and Siwei. So let me just start with the introduction quickly. Of course, the study of local operators in quantum field theory is very old and it's been going on for many decades, and many things are known. A very important generalization are extended operators. They're supported on some submanifolds, p-dimensional submanifolds, and in fact, very little is known about the correlation functions of extended operators, the algebra of extended operators, and various things of that sort. So extended operators, at least in relativistic quantum field theory, you can think about them in several ways. They can be space-like, but they can also be oriented in the time direction. And then you can think about them as a modification of the Hamiltonian on a p-1 dimensional submanifold. And this can be viewed as an impurity because you're modifying the energy functional in space on some submanifold. And also a very important consequence of this fact is that since you can view extended operators as modifications of the Hamiltonian, it's a very important fact that extended operators have a preferred normalization. So unlike local operators that have wave function renormalization, extended operators have some other types of renormalizations. I'll talk about it later. But you cannot just multiply them by a square root of 2, for instance. That will ruin the interpretation of a Hilbert space. Okay, so this is the picture. You can think about the simplest case, which is a line operator, as an impurity on some lattice. If you have a lattice model in mind, you can think about it as an impurity or a line operator in space-time. So these are valid 2 points of view in relativistic quantum field theory, and they're equivalent under weak rotation. So we cannot multiply extended operators by square root of 2, but we can do other things with them. And what other things is actually not completely known, but some things are clear. We can form a direct sum of extended operators, which are located at the same point in space, if you think about them as an impurity. So these are direct sums with positive integers. And the Hilbert space in the presence of such an impurity will be a direct sum of the Hilbert spaces corresponding to each one of them. So that's an allowed operation. I should have said that in this picture where we insert the impurity, not only the Hamiltonian changes, but potentially the Hilbert space changes, because the impurity, such as in some examples that we will see later, can have its own Hilbert space. Okay, so excellent. So we can do this integer valued sums, positive natural numbers valued sums. And another thing, unlike local operators, is that extended operators have their own coupling constants. And if there could be beta functions in the bulk, and there could be beta functions on the defect. So these are separate. There is a separate system of renormalization. There is a separate renormalization group on the defect. And even if the bulk is at a fixed point, So in most examples today, the bulk will be at some fixed point for simplification, for simplicity. The defect will not be at the fixed point generally, and it has to flow to a fixed point at long distances. So that means that if the bulk is a conformal field theory, inserting such a defect as an impurity would preserve a subgroup. And this subgroup is called the defect. This system is called the defect conformal field theory. It preserves a certain subgroup of the conformal group. And that's the infrared limit of the coupling constants on the defect. Maybe for the aficionados, I'll just mention that this transverse rotations is not a necessary symmetry of conformal defects, but it appears in all the examples we will discuss today. Okay. So what is the main question? If you are a condensed matter person or also coming from the HEPTH point of view, the very zeroth order question is whether a defect is screened. You know that the Kondo defect influenced the development of physics, perhaps in the most substantial way in the 20th century. And people have understood the renormalization group and all these things through the Kondo defect. And this was a central question of whether the infrared limit, when you tune the bulk to a fixed point and you look at the dynamics on the defect, is the defect just a sum of unit operators? And that is what I'll call screened. So if it's a finite sum of unit operators, that means that there is some quantum mechanical theory living on the defect, but it's completely decoupled from the bulk. And all the bulk point functions vanish except for the unit operator. And you can say that this defect is almost trivial. It's basically mathematical. You can say that it's trivial up to a quantum mechanical topological theory on the defect, which leads to this sum of units 1 plus 1 plus 1. That's just a degeneracy in quantum mechanics. Now, a topological defect, so if the theory has a topological extended operator, according to this definition, it's not screened. It's not literally the sum of unit operators if it's a non-trivial topological defect. So this is my terminology. In some condensed matter literature, if it flows to a topological defect, it would also be called screened because the one-point functions vanish. But I just want to be careful slightly and distinguish the case where it's a truly decoupled quantum mechanical topological theory from the case that it's a non-trivial topological defect. So it's not a necessary thing for this lecture, but for more sophisticated applications, it is necessary to distinguish these two facts. Are there any questions about the terminology of what screened means? Okay, just stop me if there are any. So as part of the review, I will give you 2 examples and 2 theorems. So I'll go over 2 theorems about defect dynamics. These are 2 rigorous theorems that have been proven. And then I'll give you 2 applications, which solve some problems in the literature. One of them, at least, is quite long-standing. And then we'll go for after the new stuff. So let's start with the first screening theorem. There is an interesting observable that you can calculate in Euclidean signature when you have a line defect. So let's discuss line defects for simplicity. And that is the partition function of the line defect on a circle. You make the space-time into Euclidean, you take space-time to be Euclidean, you make a circle, you compute the partition function. This partition function is divergent. As I said, there is no literal wave function renormalization for extended operators, but there is a divergence that's linear in the size of the circle. You can think about it as a cosmological constant term on the defect. So this divergence has to be subtracted in order to get a scheme-independent observable that has to do with defects. And so this is why there is a differential operator that acts on the logarithm of the expectation value of the circle. So this is a scheme-independent, interesting observable concerning defects. And this observable is valid whether or not the defect is already at the renormalization group fixed point. So sometimes we call this observable the defect entropy or the zero temperature quantum entropy of the defect. So it's an intrinsic observable. It's physical because the defect has a preferred normalization. And a very interesting fact is that this observable from the work on topological quantum filters. In topological quantum filters, this is the quantum dimension. And it's known that in topological filters for anyons, this object S is non-negative. And why? It's because in the theory of anyons, there is a connection to the dimension of the Hilbert space of many qubits, the number of qubits in the Hilbert space where many anyons are inserted. So there is a simple proof that this object is non-negative. However, for general defects, which are non-topological and conformal defects, this object could be negative. We will see examples today. So it could be that the quantum entropy of non-trivial defects is negative, in fact. And it makes sense because this entropy measures how many degrees of freedom are localized near the defect. And in a topological theory, there are no degrees of freedom in the bulk. So it cannot really be negative. It makes no sense. But when there are non-trivial dynamical degrees of freedom in the bulk, the defect could expel them in some way. And that's what the negative S would mean. Okay. And why are we discussing this quantum entropy? It's because it satisfies a very non-trivial inequality, which has this form. You can prove that for any defect, the renormalization group flow is such that the expectation value of the circle is a non-increasing function. It's actually decreasing function as a function of the size of the circle. You can sharpen this inequality to a true smaller inequality. And that's why I'm using it like that here. And that's of interesting constraints. So one constraint that we will see comes when we apply this inequality for completely trivial impurities, when the expectation value is 1, so S is 0, and the defect is just the unit operator. More generally, when the defect is a direct sum of unit operators, the defect entropy is the logarithm of the number of terms in the sum, and we will see some interesting applications of this inequality in the context of screen defects. You should think about this result as an extension of the famous Affleck-Ludwig result for the Kondo type defects in 1 + 1 dimensions. But this one is valid in any dimension. And there was a recent proof also using entanglement entropy by these people. So we will use this theorem shortly for some problems in defect dynamics. And now let me tell you about the second theorem.
Can I ask a question? Sorry, I'm interrupting.
Yes, sure, anytime.
So we assigned an entropy for a defect. Can we assign like a temperature for the defect? Does that make sense?
Yeah, this is the entropy of the defect at 0 temperature. You have some defect in a Hamiltonian at 0 temperature. You look at the ground state and you can assign a quantum entropy for the defect. You can ask, how do I extend it for finite temperatures? There are two choices. One is to maybe wrap the circle along the thermal circle, and the other is maybe to keep this circle space-like. I don't know if any of them satisfies a nice property.
Okay.
Okay. In my view, it's an open question. If there is some interesting notion, if there is an interesting extension of this notion to finite temperature. In 1 + 1 dimensions, the answer is decidedly yes. You can show that there is a connection between this S and the high temperature limit of the entropy, of the full entropy of the system. But in higher dimensions, I do not know if there is a useful extension to finite temperatures. It's an open problem in my mind.
Thanks.
Any other
Can I ask
questions?
a question? Yeah. Can S be negative and arbitrarily large in absolute value?
Yes, you will see today an example. Thank you for, yeah. I also thought that it cannot be possibly too negative, but we found examples where, of course, for a fixed system, if you take a fixed bulk system, most likely there is a lower bound on how negative S can be. Nobody has been able to put, but that's very reasonable. If you allow to vary the bulk system, you can get an as negative S as you like. I'll show you an example later today.
So you mean that if you fix the bulk central charge, then S cannot be arbitrarily negative?
Yeah, that's very, very likely to be true. But I don't know how to prove it, and it's an open question. And it's actually important for various applications, but I do not know how to prove that. I believe it's true. It wouldn't make sense otherwise, in my opinion.
Yeah. Thanks.
But yeah, if you vary the bulk, then you can get it as negative as possible. Any other questions? Okay. Now, the second theorem that we will use today has to do with symmetries. When we have an impurity in a Hamiltonian language, it's very clear what we mean by symmetry. So if the original Hamiltonian was invariant under some symmetry, we want the impurity and maybe the extended Hilbert space to also enjoy the action of the symmetry G and to be invariant under G. Okay, so I will say that the line defect is invariant under symmetry G if this is true. Namely, if the system with the impurity also is symmetric under G. In that situation, I will just say that the defect preserves G. Okay, that's a sensible thing to say for ordinary zero-form symmetries. It's that the Hamiltonian is still G symmetric. A very interesting fact is that if you now consider not the full line operator, but the line operator with an endpoint, it turns out that the endpoint does not have to transform under G. So while the bulk operators are assumed to transform under G, we just say that G is a faithful symmetry. Okay, the bulk operator transform linearly under G, as in all quantum mechanical systems. It turns out that endpoint operators, so the endpoints on which non-trivial defects end, they do not have to transform under G. Okay, but you can prove that the most that can happen is that they transform in a projective representation of G. Okay, if there are any questions about it, please ask. And that's my claim, that the endpoints have to furnish a projective representation of G. So that leads to a very interesting non-renormalization theorem. This projective representation cannot disappear in the infrared. So if you did some calculations in the UV when the defect is still weakly coupled, the defect hasn't flown to some strong coupling yet, and you found that endpoint operators are in a non-trivial class that has to be preserved. It cannot discontinuously jump as you do the coarse graining on the defect. And that leads to an interesting theorem, which is that even if the defect is completely screened, so it has no impact on the bulk whatsoever at long distances, it cannot be literally the unit operator. It has to have a degeneracy, which corresponds to the smallest possible representation of the projective representation at least. It may have even a higher degeneracy, but it cannot have degeneracy which is smaller than the smallest projective representation of G. So that precludes the fact that that the defect just flows to the unit operator straight on. It has to flow to some copies of the unit operator at the very least. And now we can combine the two theorems, which is the theorem about the entropy and the theorem about projective representations, which is that if you know that some defect is screened, then the ultraviolet quantum entropy. What do I mean by the ultraviolet quantum entropy? It's the partition function on a very small circle. Remember that the partition function is a monotonically decreased function as a function of the circle size. So you can easily calculate the partition function on a very small circle because usually defects are still weakly coupled in the ultraviolet. And as I said, in the infrared, the quantum dimension has to be log dmr. So if a defect is screened, this inequality has to be satisfied. And we will use this theorem, of course, in negation. So we will use that to prove that some defects cannot be screened. And this theorem is interesting even when there are no projective representations at all, because as I said, S can also be negative. So there will be interesting implications also in that case. So let's now go over the examples. I'll spend now 10 minutes just telling you for applications in simple lattice defects. These are like vacancies or extra spins. And then we'll study the new stuff. Are there any questions about the introduction? Okay.
Can I ask a question about
Yeah.
your comment on a finite line operator? So you claim that at the end you have like a point that transforms under a projective representation of the higher form symmetry group, right?
It's not higher. No, there's no higher form. This is,
I mean, like,
I'm just talking about ordinary symmetries.
okay, but this O at the blue dot transforms under the projective representation of G, right?
Yes, and G is just an
So,
ordinary symmetry. Yeah,
okay, it's not a higher form symmetry.
right.
Okay, sorry, I just concluded that.
Yeah, because I'm thinking about line defects here. So the endpoint is a local operator, so to speak, almost, except that it's in a projective rep. If you want to extend the discussion to more complicated extended operators, which are not just line defects, but maybe surface defects or something else, then you'll have to discuss other things.
Like higher representations or?
Maybe higher representations, higher symmetries. Yeah, I'm just not gonna touch it today.
Okay.
Okay, so let me just take you through examples of how this works. Let's fix the bulk fixed point to be the old Wilson-Fisher fixed point. That's just a very familiar setup. And let's study this line defect. This line defect is very easy to simulate or even experimentally cook by putting external magnetic field around a few lattice sites. So instead of putting an external magnetic field throughout the sample, which is what we usually do in graduate school, or when we study statistical mechanics, here we put an external magnetic field only at few lattice sites, and in the continuum, it looks like this kind of defect. You choose one of the directions in internal space, and you couple it to this kind of external magnetic field. And the question is what happens in the infrared? Okay, this is a very old question in condensed matter. It's called the pinning field problem. There are countless simulations and conjectures. It's interesting to apply the theorem about quantum entropy because this defect is actually asymptotically free. So the value of this magnetic field at very short distances is zero. And from the theorem about quantum entropy, it follows that the infrared entropy cannot be zero. And now remember, we said that a defect is screened. If a defect is screened, then S is zero or log n for some positive n. So therefore, this by itself already implies that this defect cannot be screened. And there was extensive discussion about it in condensed matter years ago. But it just follows immediately from this theorem. It's a non-trivial conformal defect. And we actually wrote a paper computing some of its properties. We found that it's exactly solvable in the large n limit of the Wilson-Fisher model. And we calculated a lot of its properties. And just to respond to somebody who asked about negative quantum entropy, you see in this model, it's proportional to n. So there is some number that's proportional to n, and the entropy can be as negative as you like. If you take n to be very large, the quantum entropy can be as negative as you like. And also the scaling dimension is hugely renormalized. Of the scaling dimension of the order parameter is hugely renormalized near the defect compared to the bulk. If you remember, in the bulk, it's like 0.5, and on the defect, it's 1.5. Okay, so this is the first example. The second example is more interesting. It's called the boson-Kondo problem. It's again a Wilson-Fisher fixed point. So we start from the O3 Wilson-Fisher fixed point, but now instead of just adding an external magnetic field on the lattice, we add some external atom with internal degrees of freedom in the 2s plus 1 dimensional representation of SO3. And we just coupled the Wilson-Fisher order parameter to this external atom. This SAT are the operators that act on the states of this external atom. And you can try to ask, what does this defect do? Is it screened? Is it not screened? And if you want to write it in a high energy physics friendly language, it's very similar to a Wilson line, in fact. It's a very simple toy model for Wilson lines. There is trace, there is pass ordering, there is some exponential with some matrices. So this defect really looks in the pass integral insertion like a Wilson line, except that we don't have gauge fields. We need to do the pass ordering because of the spin of the impurity. So you can have a lot of fun trying to calculate it. It turns out that this is very difficult, even if the bulk is a free field theory. And certainly if the bulk is the O3 Wilson-Fisher fixed point, it's still very difficult. But, well, there has been a lot of recent effort on understanding what it does. It's a generalization of the Kondo problem. It appears in various experiments and simulations. And one thing, I don't want to spend too much time on it. There is literature about it that you can find. One thing is that it turns out that it's solvable in the large S limit. So when this external impurity has many, many degrees of freedom, internal degrees of freedom, it turns out that it's exactly solvable and everything can be calculated. So I'm just showing you the values of the quantum entropy, the scaling dimensions of some operators, and it's some kind of semi-classical limit. So there is some, if you like this kind of stuff, you can look it up. There is an interesting semi-classical limit in the large S limit. But more interesting for our purposes today, the question that condensed matter people are most interested in is what happens when S is a half. That's the case of just an external atom with 2 degrees of freedom. It's a long-standing question. And you can use again the logic of projective representations. Remember that the Wilson-Fisher fixed point has SO3 symmetry which acts faithfully, but the endpoint operators here are projective representations. So this is maybe it's obvious from this presentation here, but if you want to have an endpoint for this operator, it cannot be in the adjoint of SO3. It has to be in the 2-dimensional representation of SO3, which is projective. It's an SU2 representation. So that allows you to calculate this class, and it leads to a non-renormalization theorem. And it means that even if the S equals a half Kondo boson problem, a boson-Kondo problem is screened, it cannot be trivial. It has to be at least, at the very least, the unit operator plus itself. And now again, you run this machine with the quantum entropy theorem and you get a contradiction. So this logic seems to settle a very old question about the boson-Kondo problem, which says that it cannot be screened, just using symmetries, projective representations, and the quantum entropy theorem. Okay, so this is the end of the warm-up before we get to the new stuff. Are there any questions about it? Okay, so this is the end of the warm-up of extended operators. And now we'll discuss the main topic of today, of what happens when we have a symmetry surface. We have a symmetry surface. This is a zero-form symmetry, very standard. Doesn't matter if it's invertible or not, but let's think about it, an invertible zero-form symmetry, and let's imagine that we cut it open. So this is the subject of today, for the first part. We just want to cut open a symmetry surface, and we get what's called a symmetry defect. Okay, so the surface itself is topological, but the boundary is non-topological. So when you take bulk operators around the boundary, which is codimension 2, you have to induce some action of the symmetry. So the question is, can we think about these endpoints or ends of symmetry defects as extended operators? What are their infrared limits? And at the end, we'll see the connection to lattice models. So just from common sense, you expect there is conformal symmetry at the boundary of a symmetry defect of a topological surface. Why? It's because as before, let's say we're in 2 + 1 dimensions for simplicity. So the boundary is a 1-dimensional line. It's the boundary of a 2-dimensional topological surface, and there is normalization group flow. So there is no renormalization group flow here because it's a topological surface, but there is a renormalization group flow when you get open. There is no unique way to cut open a symmetry surface. There might lots of free parameters in how you do that, and there is a renormalization group flow in general. So however you do that, you should reach some kind of defect fixed point with SL2R symmetry. So for instance, you can ask what happens when I scatter some bulk mode from, this is some kind of solenoid. I'll be using this word sometimes. Let me just explain why I'm using the word solenoid. You can think about this line in 2 + 1 dimensions as an Aharonov-Bohm solenoid, because if you go around it, you get a phase or a symmetry transformation. So I'm sometimes gonna call these endpoints or end lines, sorry, the boundary, I'll call it a solenoid. So there is no unique way to define these boundaries, and they have an RG flow to a fixed point. For instance, there could be some potential for scattering bulk modes. There could be some potential like that, or some potential like that, or some linear or some combination thereof. And these parameters could have renormalization group equations. And this is not even the whole story. It could be that there are very complicated many-body interactions at the boundary of the symmetry surface. So what I want to do today is to tell you a little bit about what happens what are the properties of these boundaries, and then we'll see the applications for lattice systems. Are there any questions about about the definition of the problem? Good. So let's do an example just to warm up. This example will display the main phenomenon that we will derive. Let's take a free complex boson in 2 + 1 dimensions. And the action is just going to be mean filtering. So there is just a kinetic term. And then we cut open the symmetry surface of U1 symmetry. So this theory has a U1 global symmetry under which the boson transforms by a phase. And we cut that surface open. And that means that we have a boundary. And at that boundary, there could be an interaction U. You could integrate the operator B dagger B along the boundary. That's what's written here. So here I'm, for simplicity, orienting the boundary of the symmetry surface in the time direction. So it's at x = 0, y = 0, but it's extended in time. And this is just the boundary of some half-infinite surface, which is the symmetry defect. And we are going to investigate what are the consequences of adding this parameter U on the boundary, which is some potential for the boson. A priori, it seems important because if you do scaling analysis, the delta function gives you 2 mass dimensions, B dagger B gives you 1 more, and that exactly compensates for the dimension of the measure. So a priori, U seems to be marginal, at least in free field theory. But now we have this topological symmetry surface, so the counting may be incorrect. We have to do the counting more carefully. So how do we implement into the action the fact that we have the symmetry surface? We put a flat connection. There is a flat connection everywhere. A theta = phi/2 pi. And at the origin, there is this term. So one has to do a simple calculation in QFT of understanding what is the renormalization group equation for the potential. Okay, so that's what we did. So as I said, the case of phi = 0, that's when there is no symmetry defect. It's just trivial, and this U turns out to be marginally irrelevant. It's marginal, and it turns out to be marginally irrelevant. You can see it from the beta function by plugging phi = 0, and this U goes to 0. But if you turn on the symmetry defect, the potential for the boson can be relevant or irrelevant. There's an interesting phase diagram of the possible ways of cutting open that symmetry surface. So we will discuss the fixed points. We will discuss the renormalization group fixed points of this equation now. So this is an exact result in some scheme. Of course, when you present a beta function, it depends on what scheme you're using. So here we've used a certain scheme, and in that scheme, it's exact. It's one loop exact, this answer.
So
are there any questions?
I have a question, Zohar, I have a question. So should this be periodic in phi? So you're going to extend this periodically or not?
Yes, it should, but there is some disease at phi = pi, so you have to do the calculation separately in this fundamental domain. So this answer is only valid in this domain, but you will see soon that there is a disease at pi.
Sorry, there's a what?
A disease.
A disease with phi. Okay.
At pi, when phi =
Oh,
pi,
at pi. Thank.
Yes, phi = pi. There is a certain disease, even for the boson, but it's much worse for the fermion. So this is our first warm up, and so we have to compute the phase diagram of this model between 0 and pi, and then replicate it by hand.
What is the naive periodicity? Is it pi or 2 pi?
2 pi for sure.
Oh, I see.
2 pi,
so there's another domain between pi and 2 pi?
Yes, I'll show you the full phase diagram soon.
Okay.
I'm just saying that if you want to use that beta function verbatim, literally use that beta function, you cannot use it outside of this interval.
Oh, okay.
Yeah,
So this is one loop exact.
Go ahead.
Yeah, I'm sorry. Yes, I'm listening.
I have a cousin of Greg's question. If I try to make phi negative, I would guess that near phi equals 0, everything is nice and smooth.
Yes, you're right.
Then
You can
the
extend
beta
it.
function is not.
You're right. This beta function is only valid in this domain,
Right.
but there is an issue also at phi equals 0. You'll see in a second. There
phi
are
equals
two
0 means
special points. You'll see that there is some small issue at phi equals 0 and some bigger issue at phi equals pi.
Okay.
And the full phase diagram has to be glued by hand from what you learn from this domain. The calculation is subtle and it's only done in this domain. So I can explain how the calculation is done if there is interest, but it's not a high priority for me now. It's explained in detail in the paper. Okay. So if you just analyze that beta function, you find two fixed points. It's a quadratic equation, so nobody's shocked. So there is one fixed point that is stable under the renormalization
ברגע
group.
זה היא מתקשרת. והיא גם אמרה, האפוינטמנט שלך הוא scheduled. I'm only calling to compare. It's not scheduled.
Yeah. So there are two renormalization group fixed points. There is a stable fixed point where there is an irrelevant operator of this scaling dimension. So the bulk scalar becomes essentially irrelevant. And there is an unstable fixed point under the renormalization group with this scaling dimension. And the issue that I mentioned that occurs when capital phi is equal to pi is that this makes no sense. You cannot have an operator of dimension 0. It violates unitarity. So the unstable fixed point disappears. There is some discontinuity at phi equals pi. Another very important, physically important quantity is the current. So the current by scaling symmetry has to decay linearly, has to decay one over the distance, and one has to compute, is there a current in the vacuum? It's a little weird to discuss this question, but I'll explain the physical intuition. And it turns out that there is a current in the vacuum, and also you can try to compute this quantum entropy. It turns out that there is a simple formula for the quantum entropy. So let's first go over the quantum entropy. So there are two fixed points under the renormalization group flow. This is now displayed in the full fundamental domain between 0 and 2 pi, coming back to Greg's question. And there are two fixed points. They merge at phi equals to 0. And that's why there is a small issue. There is a small issue even at 0 because two fixed points merge. But as you go towards pi, which is here, this quantum entropy just diverges while this stays more or less unchanged. It's almost constant. It's just a small positive number. And so this is the full phase diagram. There are two fixed points, and there is a renormalization group flow from the yellow to the blue line. Just that at pi there is an issue. There is an asymptote. And more interestingly, we can calculate the current. So what is this little a? This little a is the current. So you have an impurity, which is a symmetry defect at x equals y equals to 0. And it turns out that that current starts circulating around the impurity in the vacuum. You probably heard of some important theorems of Bloch from a century ago, or somewhat less, that there cannot be a current in the vacuum. This is not true. So here is a counterexample. Another famous counterexample is when you put a superconductor on a torus. But here here it's a completely different story. There is no superconductor and there is no torus. All we did is to put an impurity, and it led to a current circulating everywhere in space, decaying as the distance. And that's the magnitude of the current at the infrared stable fixed point. Now, there is something here we don't completely understand of why does the Aronoff-Bohm flux rip particles from the vacuum? So the current proceeds everywhere. And this is what I'm going to say in this slide. Of course, if you study the Aronoff-Bohm flux in quantum mechanics, where particles are not created from the vacuum, We know that particles start going around the Aronoff-Bohm flux. That's a very old and well-known phenomenon. But here there is a different story. It turns out that even in the vacuum, particles are ripped off from the vacuum. It's like in the Schwinger effect, but here there is no electric field, only an Aronoff-Bohm solenoid. So it turns out that an Aronoff-Bohm solenoid at the origin is enough to rip off particles far away from the vacuum, and they start going around, and the current vanishes when, oh, sorry, it's not theta, it's phi. And the current vanishes at a half flux, which of course makes sense because there is time reversal symmetry at a half flux. Okay, so it sounds, there is some similarity with the Aronoff-Bohm phenomenon, but it's really different because we are saying that there is a current in the vacuum just because of the solenoid. Are there any questions about the boson? Now I'll tell you what happens with the fermion that is even more confusing.
Can I add something quick?
Sure.
So you mentioned that at phi equals pi, one of the scaling dimensions was 0, right?
Yeah, that's the unstable fixed point. It just goes to infinity. Yes.
Should I think of that as another ground state, like maybe time reversal is spontaneously broken or something like that?
Yeah,
And that's why...
yeah. You can think. So here I display the current only if the renormalization group flow at the Aronoff-Bohm solenoid leads to the stable fixed point. If the renormalization group flow is fine-tuned to lead to the unstable fixed point, then the current would actually diverge at pi. And also it will go to minus infinity. So there will be two, so the graph would be essentially like that. It would go to plus infinity and then from minus infinity.
Okay, thanks.
So yeah, you can even have infinite current at phi equals pi if you tune to the unstable fixed point. One physical thing that's missing here is some kind of explanation of why particles are ripped from the vacuum. I can discuss it later. Now, let me just tell you the answer for the fermion. So the Dirac fermion is even more confusing because when the flux is exactly pi, there is an exactly marginal operator on the defect. There is no exactly marginal operator in the bulk, of course. It's just the theory of a single free Dirac fermion. But on the defect, it turns out that phi dagger phi suddenly becomes exactly dimension 1, while in the bulk it's dimension 2. And it's exactly marginal. And that's the red line. There is a conformal manifold. I don't know if this conformal manifold is actually compact or not when you compute the Zamolodchikov metric. I think somebody did that, but I forgot what the answer is. So the blue line is the stable infrared fixed point. The yellow line is an unstable infrared fixed point, and they can kind of get exchanged. So there is a delicate phase transition when flux equals to pi, that the stable and the unstable fixed point get exchanged. And in fact, you cannot even predict the current at pi because there is an exactly marginal operator. You can get anything you want between these two values of 1/4 pi and negative 1/4 pi. And time reversal symmetry acts on this exactly marginal operator. Okay, so this is the fermion. So this finishes the QFT computations. Now
Sorry,
we'll
I have
go
a question about the fermion. What is the definition of the defect here? It says you just cut open your symmetry defect, or you also add psi dagger psi on the defect?
It's not up to you. It's not up to you because as soon as you cut open the defect, whether or not you add psi dagger psi, it's not up to you anymore.
Well, my question is that in
it's an invariant
case, that was classically marginal, while in the fermion case is classically relevant. So
no, but look at that. Consider the following fact. It's classically marginal when U is 0. When phi is 0. It's classically marginal when there is no symmetry defect. As soon as there is a symmetry defect, the scaling dimensions of defect operators get strongly renormalized.
I see.
So, for instance, this is the scaling dimension of some defect operator.
I see.
So it doesn't matter if you want to edit, you don't want to edit, it doesn't matter. The phase diagram that I'm showing is like completely general. These are the only two things you can find. Okay?
I see. Thanks.
Unless you do fine tuning, you'll end up on the blue line. That you know for sure. And you can ask what will happen at pi. I cannot answer that question because there is an exactly marginal operator. So the large volume limit is not well defined unless you tell me what you do exactly. when you cut the symmetry surface open. I can only tell you that if you don't fine-tune, you'll end up on the blue line, except for phi equals pi. I cannot predict what will happen here.
Can I ask a very
Okay,
naive question?
sure.
So there is like a symmetry in the phase diagram, both for the case of boson and the fermion. Can we view this symmetry as some manifestation or like a version of an electric magnetic duality?
No, it's just the U1. I'm talking about the symmetry. I'm talking about
Yeah,
the
but
U1 symmetry defect.
yeah, but like not necessarily for a gauge theory, but like there is a certain transformation for the flux and the current that you can do, which lands you on the same spots in terms of the phase diagram.
You're seeing some duality in this phase diagram? That's what you're saying?
Yeah, like I mean, this blue line in the left and the right are symmetrical. I can
Oh, this
cook
is,
up
yeah,
some
this is time reversal.
transformation.
This is a time reversal
Yeah.
symmetry. This is just time reversal symmetry.
Okay.
Yeah.
Okay.
The blue line here and the blue line here are mapped by flipping the sign of phi around pi and time reversal. Yeah. Even
I
charge,
was wondering
even charge conjugation. You don't even need time reversal. Just charge conjugation would do. Okay. So now,
I
yes.
have a big question. So along the red line, phi is pi. So you have both the U1 and the time reversal symmetry. Now there's a mixed anomaly between the two, what is known as parity anomaly. I'm just curious, does it play any role in your story?
Yeah, I think it plays a big role, but it was not in the paper. We're working on it now with Brandon and Fyodor. We're trying to understand the anomalies on the defect.
Okay, nice. Okay. Looking forward to that.
So let me just now tell you why this is important in lattice models. So this is just an example, okay? We went over many examples. So when you have a lattice model, this is a lattice model where okay, let me just define the cast of characters. There are fermion operator C on every lattice site, and the reason that you see two layers is just for visual simplicity. Actually, each of these fermion has two indices, up and down, and the sigma matrices acts on this inner index, up and down. So there is each C is basically a vector of two different fermion operators, quantum mechanical fermion operators, and the sigma matrices act on this internal space. So just for the simplicity of visualization, we created this figure where the blue and the black represent the up component and the down component of the C's. And the lines, the black lines, red lines, yellow lines represent interactions. The interactions are mediated by these three terms. Okay? And the symbols A and B are because when you do a rotation on the lattice, you can choose to do a rotation around a plaquette or a rotation around the vertex. We will discuss both of them very soon, of how these rotations act. So A and B are plaquette and vertex centered rotations. So this is a very simple model. It's actually quadratic. It's exactly solvable. I'm showing it just for the sake of demonstration of some simple facts. Well, so let's go over the phase diagram of this model. It has only one parameter, m, and you can just tune this parameter from minus infinity to infinity and see what happens. So everywhere outside of -1, 0, and +1, this model is gapped. At -1, 0, and 1, it's gapless. At -1 and 1, it has one Dirac fermion, though it's not at the same point in the Brillouin zone. Here, the massless Dirac fermion is at pi pi, and here the massless Dirac fermion is at 0, 0. And at 0, when the mass vanishes, there are actually two Dirac fermions at pi 0 and 0 pi. Okay, so this is, if you just diagonalize this Hamiltonian, you'll see that there is a continuum Dirac fermion at low energies at the special values -1, 0, 1. This toy model is called the QWZ model, Chi Wu Zheng. Okay. So this is what I'm saying here. The long distance theory is just a free Dirac fermion. It's a quadratic model. There is nothing fancy. And an interesting question is, how do lattice symmetries map to the continuum? So we have some symmetries on the lattice, like rotations, translations. They have to act on this continuum fermion. But it turns out that they do not act on these continuum fermions in the simplest possible way. There is a certain group homomorphism So the group homomorphism is asking how do lattice translations and rotations map to continuum symmetries of the infrared massless fermion? Okay, it's a well-defined question. And we can ask, for instance, what about rotations? So this symbol O, M is just 4. This model has a 4-fold rotation symmetry. So let's consider the generator of this 4-fold rotation symmetry. And let's do a rotation around either a plaquette or a vertex. And let's tune the mass to be either -1, 0, or +1, so that we have a massless fermion in the continuum. And we denote this massless fermion in the continuum by capital psi. Capital psi that's associated to some point on the Brillouin zone where these two shells met, when these two bands met. So we just tune to one of those points. And we ask, how do lattice rotations act? So in addition to the usual rotation that you expect in the continuum, when you do a rotation in the continuum, of course, a Dirac fermion transforms with sigma matrices. That's just the generator of rotations in the continuum. The thing is that you get another U1 phase, which is labeled by a topological number S naught. It's not topological in a technical sense. We just call it topological sometimes. Maybe it's a slight abuse of language. It's an interesting parameter for sure. And similarly for translations, the translations act in the continuum by multiplying the fermion by a certain phase. Okay, so the lesson here is that rotations and translations in the continuum act by an additional U1 transformation in addition to the geometrical action of rotations and translations. Okay. Now, the thing is you have to calculate this S0. You have to calculate how lattice rotations act on the continuum fermion. This is, again, I'll call it topological by abuse of language. You have to calculate these topological quantum numbers because they're very important in determining how the symmetries in the ultraviolet map to the symmetries in the infrared. So it's a simple calculation. It's a quadratic model. It's very well known in the lattice, in the condensed matter community, that lattice symmetries may induce unitary actions in the continuum limit. This is behind all these models with LSM theorems. It's very common in topological insulators. It was also recently discussed by Mong and Nari. And so here we just calculate these quantum numbers S for lattice for vertex centered rotations and plaquette centered rotations and vertex centered rotations. Yeah.
For translations, I understand that it's surprising, but for rotations, isn't it obvious because your lattice fermion is a scalar and your continuum fermion is a fermion? Your continuum fermion is a spinor?
I think in this model it's obvious for both. So I don't know. I would say it's obvious
even
for both.
a priori, before you say anything, your lattice operator is a scalar of rotation.
Yes.
And your continuum operator, it must be a spinor.
Yes.
So that already tells you that the Z4 of rotation has to act differently.
That's true. There are lattice models we
That
studied.
is independent of what the Hamiltonian is.
Yeah, that is true. That tells you how S0 must be quantized, though. So there are lattice models where lattice rotations are like -1 to the F. When you do a full 360 degrees, you get -1 to the F.
No, there is a question of -1 to the F. This is more detailed.
Yes.
The -1 to the F would tell you that continuum rotation by 90 degrees is an order 8 operator rather than order 4.
Yes.
But all I'm saying is that on the lattice, it's order 0, right? It's order 1s, right? Because it doesn't do anything.
Yeah, I think both things are just obvious. So the translations is obvious because the fermions do not appear at 0, 0 in the Brillouin zone. So the actual massless fermions in the continuum are oscillating on the lattice. So I think both things are obvious. Yeah, so you can just calculate this topological numbers S for both cases. And you can think about it as a topological twist, a la the topological twist that Witten did in some years ago. It just means that lattice rotations, for instance, do not map to continuum rotations. They map to continuum rotations plus an ordinary U1. And that's very reminiscent of mixing continuum rotations with U1 is a little bit reminiscent of topological theory. So I just wanted to make this analogy for those who like that stuff. So lattice rotations look like twisted rotations in the continuum in the sense of topological twisting. And this has implications for when electrons move on a crystal with defects. And that was the motivation for our paper, because it's an interesting question in condensed matter. If you take an electron that's moving on a regular lattice, this is just another version of the same lattice model that I had before. If you take an electron moving on an ordinary lattice, I told you the answer is a free massless fermion in the continuum if you appropriately the parameters. An interesting question is what happens if there are lattice defects? So here is a picture with one lattice defect. It's called a disclination in the crystalline defects literature. It's a special point which has 3 neighbors rather than 4 neighbors, as you can compare it with all the other points. So when a fermion would move on this geometry, we would naively think that the continuum way to model this fermion, when let's say m equals to 0 or m equals -1, is to put a conical defect, because that's what it is in the continuum. But because the symmetry in the continuum is twisted, it's not true. And our previous discussion leads to the fact that there must be particle creation. So we're led to make a prediction that when electrons move on a crystal with defects, like disclinations, there must be particle creations very far away, and there will be a persistent current circulating around the disclination. So now the whole story kind of finished. One makes a prediction that around disclinations there is a persistent ground state current that will just swirl around at 0 temperature. And the question is if it's true. Can we measure it? And that's the measurement. So it works precisely. The clean lattice is without a disclination. That's the current that you measure if you put a symmetry defect without a disclination. Sorry, the black line is the clean lattice, and the blue line is the lattice with a disclination. And when you just make a pure disclination without adding local symmetry defect flux, you see that there is a current. And you can even measure this topological quantum number from the displacement between these 2 lines. Because what the disclination does is to create a current, which you can basically backtrack to measure this as naught. And m is 4 in this lattice model. And you can then compare it to the theory calculations, and it exactly works.
Sorry,
So
can I ask a quick question?
Sure.
In the figure, those different lines with the same color, sorry, not this figure, but the plot you just showed. At what point are you measuring this current, like the maximum amplitude one?
Yeah, so if you make it just a clean disclination, like you just take a lattice, you make the cleanest possible disclination, right, of just removing 1/3 of the lattice and reconnecting the lattice, then you have to make a measurement here. You can make a measurement here, or here, it's the same, okay? So
But
if
the
the lattice
different-
was clean, if the lattice was perfectly clean, there would be no current. And
Right.
here you observe you observe a current in the ground state circling around the disclination. And it's due to the twisting of the symmetry, and it's due to the fact that the stable fixed point of the renormalization group, there was a current
Yes,
when there
sorry.
was symmetry defect.
I mean, like the different curves you show here,
Yes.
they correspond to different measurement places for this current.
Yeah, so they correspond to making a disclination, and on top of that, you can also add an Aronoff bomb solenoid at the tip of the disclination.
Okay.
So they correspond to just adding the exact same monodromy defect on top of the disclination, and you can see that the 2 curves are shifted with respect to each other, and it just confirms, say, experimentally in quotation marks,
All right.
the fact that the symmetry in the infrared is twisted.
Okay, thanks.
Okay. Let me just summarize with some questions. So let me just say that this measurement exactly coincides with the theory. It agrees with the value of S naught in the theory. And more importantly, it agrees with the predictions from the calculations in quantum field theory of currents in the vacuum when there is a symmetry defect. But I must say that with the full curve, I don't think we believe that we have reached the infinite volume limit. So this exact shape does not yet completely agree with quantum field theory. And especially interesting is what about this line? can we see this exactly marginal operator? I remember it. I told you that. You remember I told you that there is an exactly marginal operator at a half flux. So somewhere here there should be a signature of that, but we did not see it yet numerically. We are probably a little far away from the infinite volume limit, which is very, very subtle when there isn't exactly marginal operator. But this measurement worked out very well. It's exactly a quarter of 0.5, which is the value of S naught for this particular plot. Okay, so just to summarize, we've seen constraints from topology and monotonicity theorems on defects in quantum field theory. I try to give arguments about the pinning field problem, the boson-Kondo problem, using these ideas of symmetries and RG monotonicity. We discussed SL2R symmetry in the infrared limit of open symmetry defects. We discussed the fixed points for bosons and free fermions. Some open questions. It seems we have not been able to find examples of symmetry defects where the quantum entropy was negative. Perhaps that's of interest to some people in the audience. For the pinning field defect, maybe you remember it was arbitrarily negative. But for symmetry defect, when we computed the quantum entropy, in many examples, we never found that it's negative. So that leads to an interesting question. Can it be negative for symmetry defects? And okay, then there was this whole story about the lattice continuum correspondence and how we can, and why we predict the disclinations and dislocations lead to persistent currents circulating around the defects. So that should be important for crystalline defects in some systems which are gapless. Thank you so much. That's the end.
Hey, thank you for the nice talk. Are there questions?
See if there's. Okay.
I see one raised hand. Oh, no.
No.
Maybe I can start with a question. So when you say
Yes.
that there is a current in the vacuum, you really mean that the current is a non-trivial vacuum expectation value, right?
That what?
The current is a non-trivial vacuum expectation value. The U1 current.
Yeah. Yeah, it means that around this disclination, electrons go anti-clockwise, positrons go clockwise. So there is a total current and there is a total energy density, but there is no total charge. So actually the total charge
that was the
vanishes.
next question. Okay. The total charge vanishes. So.
There no, yeah. In the crystalline topological phases, which are gapped, I didn't discuss them. I don't have time to discuss all these things. There are gap phases here in between these gapless points. Those are the phases which have crystalline topological response. In those phases, there is some charge accumulation on disclinations, but no currents. We have no charge density away from the disclination, only currents.
The charge, I guess,
because
has to vanish because the defect preserves the symmetry, right?
I don't know. There could have been some charge density here. I don't know why there isn't. It's just fact of life. There is a current of electrons and positrons going exactly opposite. So there is no total charge, but there is a current and energy density. We actually measured also the energy density in the lattice, and it agrees with the continuum prediction. There is a similar diagram in the paper with the exact same shift of the two graphs with respect to each other. So it seems to agree. The picture seems to agree. It does seem like there is particle creation due to disclinations.
Okay, thanks. Other questions?
Can I make a question?